Now we are going to discuss what is the difference between the sigma MOS and pi MOS. Now the first difference is that sigma MOS are formed by of atomic orbital which are pointing along the internuclear axis, whereas pi MOS are formed by atomic orbitals which are perpendicular to the internuclear axis, which are perpendicular internuclear axis. Then next one, in sigma MS the electron density is concentrated along the nucleus density is concentrated it's 0. It is concentrated in two nuclei above and below the internuclear axis. Or famous orbital or symmetric along the internuclear axis. Whereas all sigma antibonding orbitals are symmetric. Whereas pi MOS symmetric along internuclear axis. Whereas MOS are symmetric so So this is the main difference between the sigma MOS and pi MOS. Now let's discuss what is the difference between the bonding and anti-bonding molecular orbital. So as with the first, we know that the first difference in bonding molecular orbital and anti-bonding molecular orbital is that bonding molecular orbital obtained due to combination of wave function of atomic orbital whereas anti-bonding molecular orbital formed by combination of here we can say that addition of wave function where combination of subtraction of wave function of orbital atomic orbital. The bonding is take place, the actual bonding is take place whereas in antibonding molecular orbital no bonding is resulted. No bonding is resulted. They have a lower energy than that of antibonding orbitals, of combining orbitals. Whereas they have a higher energy than that of combination of atomic orbital now the next one, it is stable, it is unstable, nuclear repulsion is shielded, whereas in antibonding molecular orbital nuclear repulsion is not shielded. Is not shielded. Then there is no node but positive overlap. There is a node perpendicular to the internuclear axis. One is that electron density is concentrated along the between the nuclei. Electron density is away from internuclear region. So these are the main differences between the bonding and antibonding molecular orbital. As we know that the bonding orbital has a less energy than the antibonding molecular orbital. So here also there is a node formation in antibonding molecular orbital, whereas there is a no any node formation in bonding molecular orbital. So let's discuss the molecular energy level diagram for homonuclear diatomic molecule. In that we are going to discuss 2 to 3 examples of this homonuclear diatomic molecule. First we are going to discuss. This is an hydrogen. The electron configuration is 1s1, but here there is a plus charge. So there will be the 2 electron of 2 respective hydrogen atom. So the plus 1 is getting. So this is a 2 hydrogen atom, and there is a 2 electron for 1 for each hydrogen atom. But here is a plus charge. So the only 1 electron in hydrogen. So here it consists 2 hydrogen with 1 electron. Now the combination of hydrogen, one is atomic orbital, gives 2 MOS, that is molecular orbital. That is 1s and antibonding orbital. Just the energy level diagram for this H2 plus ion. Atomic orbital. This is also atomic orbital. This is a molecular orbital. There is a 1 electron here also. Is a sigma ns, that is antibonding molecular orbital. So that is a star ns. H2 plus, that is 1s. Is for H and that is for H plus. So there will be no electron, because in hydrogen there is a 1 electron and plus sign means that is minus 1 minus 1 0. So that's why there will be no electron here. So energy we can calculate from this diagram, that is the energy in volt. So we can write that energy volt is equal to number of electron in bonding molecular orbital into minus beta, that is we already discussed in linear combination of atomic orbital, that is beta, and the number of electron in antibonding molecular orbital, that is that is This is also known as a stabilization energy. The bonding molecular orbital is 1s and anti-bonding, that is a 1s star. So here there is some stabilization in from 1s to 1s star orbital. So that's, we can say that the beta is an stabilization energy for the H2. So from that we can calculate the bond order. So is equal to number of electron in bonding molecular orbital. Bond order is equal to number of electron in bonding molecular orbital minus number of electron in anti-bonding molecular orbital. If you put the value of this H2 atom, then half into bonding molecular orbital, we know that there is only one electron, that is a bonding orbital. So that is 1 minus number of antibonding. Here for antibonding there will be no any electron. So antibonding means that is in star, so there will be the empty, so the number of electron is 0. So the total calculation is that means the bond order is nothing but the, so bond order we can say that bond order is the number of bond between two molecules to form molecule. So bond order is nothing but the number of bond formed between the two atoms, between two atoms to form molecule. So we can say that the bond order is equal to the number of bond. So this is all about the formation of He2 plus ion. In that there is the bond order of this He2, that is a half. So it is a paramagnetic, because it is not a even bond order, means that there is a spin in that, so that is a unpaired electrons here. So that's why the H2 plus ion is an paramagnetic one. Now let's discuss the next H2 molecule. Now here, that is in H2 molecule, as we know that each hydrogen atom has one electron. So there is a two hydrogen atom, means there is a two electron in each 1s orbital of respective hydrogen atom. Now one electron is in bonding molecular orbital and another is an anti-bonding molecular orbital of hydrogen atoms. As we know that the bonding molecular orbital electron has a lower energy than anti-bonding molecular orbital. So let's see the diagram of this MO energy level diagram for H2 ion. Here that is antibonding molecular orbital. Here also antibonding molecular orbital, that is sigma 1s, that is sigma 1s, that is H2. Here one hydrogen, here also one hydrogen, that is one hydrogen, here also one hydrogen, that is a two. MO energy level diagram. For H2 molecule. So the energy lower during the formation of this H2 molecule, we can calculate that bond order, that is number of as we know that the bonding molecular orbital minus number of antibonding molecular orbital. So in that we can write here number of bonding molecular orbital. So that is here one is diamagnetic and stable. All electrons are paired here, so that's why one is a bond order, means that the electrons are paired, so that's why the H2 is diamagnetic and stable one. Now energy involved in this H2 molecule that we can calculate it as energy involved that is, we know that there is a 2 so that is a minus 2b. So this is all about the H2 molecule. Now let's discuss the next. There is a 2 helium atom. One helium have 2 electrons. Now here there is a 4 electron, but the plus sign, that is a 3 electron. So here that is antibonding orbital, that is molecular orbital. Here also there is antibonding orbital. There is a 1 helium atom. Here also there is a 1 helium atom, that is plus ion here. If we see, there is a total of 3 electrons. So this 3 electron we can distribute as like here, that is antibonding. There will be the 2 electron, that is 1s. There will be the 3 electron, but here only 2 electron can accommodate here, and the 1 is goes, that is 3 electron, 2 is occupied here, and 1 is goes to antibonding molecular orbital, and that is 2s orbital. So here there will be the 1 electron, here these 2 electrons. Now what about the energy involved in the helium plus ion? Now we know that the energy involved for helium plus ions, that is 2 electrons for bonding and 1 plus for beta. So that is the stabilization energy of helium to ion. And what is the bond order of that helium? Now we will discuss. As we know that the bond order is nothing but the half into number of bonding molecular orbital minus number of antibonding molecular orbital. So here as per our calculation, here half into number of bonding of molecular orbital, that is 2, and number of antibonding molecular orbital. Here we can say that is equal to 1. So you have paramagnetic, so the He2 plus ion is paramagnetic. You can write here also paramagnetic, and it is not a stable one. Helium diatomic molecule. So here that is a He2 molecule. As we know that in helium, 1 helium have 2 electrons, so 2 helium have 4 electrons. So that is in 4 electrons here. Now the distribution of electron is as like, there is antibonding molecular orbital. This is also antibonding molecular orbital. This is a molecular orbital here. Now here there is a 2 electron, that is from 1s and 2s. Again there is a 2 electron from bonding and antibonding molecular orbital. As we know that there is a 2 electron in bonding and 2 electron in antibonding molecular orbital. Bonding molecular orbital has a less energy than antibonding molecular orbital. So there will be the 4 electron, 2 electron get shifted into antibonding molecular orbital of helium atom. Now let's discuss what is the energy involved in helium atom, helium molecule. So that's there will be the 2 electron and the 0. So 0 stabilization energy is for He2 molecule, and the bond order, as we know that the bond order is nothing but the half into number of bonding and minus antibonding molecular orbital. Here that is the stabilization of He2 molecule, that is 0. So we can conclude that that is a bonding molecular orbital 2 and antibonding molecular orbital is 2. So that will be the 0. So it is not stable one and it does not exist. So it is not stable and not exist, because the bond order is 0 means the number of bonds formed between the molecule is 0. So that there will be no bond formation means that there is no existence of that particular molecule. So the bond order of He2 molecule, that is 0. So this is all about the MO energy level diagram for He2 molecule. Now we will stop here. In next lecture we are going to discuss the next point. Thank you.